Do you believe that Linux kernel hacks people? If you are an aspiring Linux engineer and you want to apply some concepts that you recently learned, you will be fooled by the Linux kernel more often. Today we are going to see such a topic. It is called copy on write or simply COW. To understand it, you should have familiarization with virtual memory and how processes are created in Linux. If you know them already, you can skip next two sections. In this video, we are going to see virtual memory fundamentals, Linux process creation flow, how Linux handles memory during process creation, and at the end, we will have a working demo of this concept copy and write. Virtual memory fundamentals. For a running program, all its variables are stored in RAM, also known as memory. This memory is addressed byte by byte. For example, if your machine is having 4 GB of memory, all of its address space are addressed from 0 to 429 crore 49 lakh 67,293. So, if you are having a program like this, the variable A is stored in an address in the above mentioned range. Thus, when you print the address, it should print one of the address in the range, but that is not the case. Linux introduces an abstract layer. For every program, Linux creates a table. On the left column, it assigns a random number. On the right column, it puts the actual RAM address. The program works on the address on the left column. It has no knowledge about the existence of the right column. The address on the left side is called as virtual address and the address on the right side is called as physical address. In case this program wants to modify the variable A, it will try to update the address hex 7000. Under the hood, Linux kernel will understand that the program wants to modify hex 5000 and updates that location in RAM. If you want to learn more about Linux virtual memory and why it is implemented in such a way, please leave a comment. I will create a full video on Linux virtual memory. Process creation workflow. In Linux, a new process is created with fork system call. Only a running process can invoke fork system call to create a new process. When a process invokes fork, all of its resources, including the page table, will be duplicated and given to the child process. If our process A calls fork, a new process will be created and duplicate copy of process A's page table will be given to second process. Now if process B modifies the address hex 7000, it will reflect in process A also. The variable A in process A will be updated. This is undesirable. So to avoid this problem, Linux allocates new physical memory and updates B's page table before assigning that to process B. So if process B updates the location hex 7000, it will actually update the hex 6000 address in the memory. We just touched surface of the Linux process management. Subscribe to our channel to not to miss the detailed video on fork and Linux process management. The hack, copy and write. The page table duplication and new memory allocation during fork is a costly operation. This will delay the overall process creation time and in most cases this allocated memory will go unused. In that case, the heavy lifting done by the kernel goes wasted. So to optimize this, Linux developers introduce this hack, copy and write. As per this hack, Linux kernel will not allocate new memory for the new process page table. Instead, it will assign the duplicate of the parent's page table as is with just one modification. The kernel will just mark the pages as copy and write before assigning. So the new process will continue using the physical address of the parent. Only when the new process tries to update the value, new memory will be allocated and the corresponding page will be updated in the page table. As the new memory is copied only upon a write, this concept is called as copy on write. As per copy and write, two processes could point to same physical address. Let us verify this behavior in this demo. For that, first we need a way to convert virtual address to physical address. Linux has a special file /proc_pid pagemap which will have the address table information of the process. I have written a C program that will get PID and virtual address of any process and print the corresponding physical address using the pagemap file. Link to the source code of that program is given in the description. Now let's write a simple C program that will call fork to span a new process. After that, from both parent and child, their PID and the address of the variable A are printed. We should make sure there are no writes happen after the fork. Now if I feed PID of both process and the virtual address to the get physical address program, we should see same physical address. Here we use the address of the global variable because we should make sure no write occurs on the memory segment. So only the data segment remains intact. So in this demo we are using a variable which is residing in the data section. Hope you learned some new concepts today in a fun-filled way. Take it as a start and do your own experiment and share your findings in the comment below. Actual Linux learning depends on a lots of hands-on, and don't forget to subscribe to our channel. A lot more interesting stuffs are lined up for you.